This is the first lecture of the course, which is called Brownian Motion and Stochastic Calculus, and this is a part of the special one-year master program in Geneva University in math, which is devoted to statistical physics, mostly in 2D, but not only. And let me start with some general remarks about this course, like the very first chapter or paragraph will be some introduction and reminders. So let me try to say briefly what's that about. Probably most of you already heard this saying Brownian motion, and I fairly believe that some of you actually even, took some course on this, or maybe heard some mini course, attended mini course, etc. So the Brownian motion is a continuous object, so that's important. I mean, in other courses of this program, basically what we or you deal with is some model in discrete, like the Eisen model presented by Ivan day before yesterday, which is okay, some discrete system, maybe just of finite size, maybe of infinite size, then the set of faces is countable anyway. And then the questions we are interested in are what happens in the limit. If we can describe the limit of this complicated physical system, or maybe not that complicated, anyway, when the mesh size is very small. So this is, this is the basic framework of all this business. Okay, and then there are good news about this course and bad news. Good news are as follows. So Brownian motion is a continuum limit of the simplest possible discrete, if you wish to say, system of some discrete evolution, discrete behavior, which is a simple random walk. Just imagine you are in a city that you are not very familiar with, so you have no idea to where to go, and you just start do this totally at random. So you have some trajectory. So simple random walk. Okay, imagine this is a very regular city, like Manhattan, and then you just start moving there uniformly at random at each side. So you do some, you go along some path, which is a random path. And of course, it's rather rough. And if you are sitting there or behind, so what you see is, okay, you can think about some limit of this, which is a continuous trajectory. So the Brownian motion is here. So this is just the name for this evolution in continuum. And as I said, okay, this is the simplest possible system. And so you can expect that many things actually can be derived and proven and so forth and so on. Well, this is good news about the course, that we are dealing with something simple. The bad news are in the word calculus. So, okay, we are going to prove something rigorously. It's going to be epsilons and deltas. I'm sorry for this. From this perspective, maybe this is, well, this should be said, it's rather technical course. And so we really would like to prove things about this object. And on the contrary, with other courses, we are going to do this in continuum. So the basic idea is that here we are not that much interested in the convergence theorem. Of course, it will be there in the course. But the general idea is that we study this object and some objects developed from it in continuum. And because of that, of course, it increases the complexity. For those who are participating in the master program, next term, you will have some courses that prove convergence of some more complicated systems here, like the Eisen model or maybe something else, dominoes, etc., to their continuum limits. And there, quite often, this continuum limit is constructed using Brownian motion. So you should think about the Brownian motion as the basic building block of everything in continuum. So this is the very basic element, like in the first course of probability, the normal distribution is the very basic block for many things. Okay? So then another small comment, why the name Brownian? Again, I think that many of you actually know the answer. So this is due to Robert Brown, who in 1827 described the motion of a big particle, actually a grain of pollen, in water. So he just, made some observations in a microscope, and again, so it's pity I cannot show you an experiment like Ivan did, but just imagine this virtual experiment. So you just see, watch on a drop of water in a microscope, and there is actually something that is much larger than the molecules of water moving there. And so, okay, he made some pictures, and it was some random movement. You should remember that at that time it was not clear that actually molecules of water do exist. So, and from some perspective, it was one of their very good motivations to develop a strict theory of all that. Okay, but now, okay, we are much more trained and all that, and of course, what's happened, at least what is the contemporary explanation, is that there is this huge grain of pollen, and it's bumped from every side by molecules of water, which are moving chaotically, and then it produces this movement. And okay, here there are only positions after, I don't remember, after some fixed amount of time. So this is an approximation to the real trajectory, which we expect to be a Brownian motion. Okay, and it should be said that, of course, he was not the first who observed this effect. So there were other guys before, but by some reason, as usual with the names of every law, so by some reason, this is fixed for him. Okay, good. So just to summarize, the general idea is that we are interested in this object in continuum. So we are going to construct it, to study its properties, etc. But the motivation you should have in mind is that basically it is the limit of some simpler things, I mean technically simpler things in this group. Okay, so then let me start with the set of reminders on on the basic probability course. I'm sorry if I'm boring, but just to fix that we are on the same wave. So given a random variable, so what is the random variable? This is a mapping from some space, which is called probability space omega, say to R, or maybe to some other metric space, which is measurable with respect to Borel sigma algebra there and some sigma algebra there. So actually here there is sigma algebra and probability measure. So given such an object, a random variable, there is a natural function assigned to it. Actually, there are many. So one of those is just the distribution function, but that's not what I'm going to talk about. So what I'm going to remind you is that there is an object which is called characteristic functions. So what's that? I put here z because later on t is going to be a time. So let it be, to distinguish two variables, let it be z, though it's going to be real. So this is just an expectation of I, z, psi. Z is real. In principle, you can, with no harm, to think about this, about z as being in the upper half plane. So still, this is less than 1, and so there are no problems with convergence. Okay, so this is the characteristic function, and what are the basic properties? The basic properties are just it's continuous. It has 0 limits at infinities. Actually, it means it's uniformly continuous. Then, well, its value at the origin is 1. And then, if this variable has moments, then you can refine this behavior. You can say what are the further terms. So basically, if it has the second moment, so if the integral of xi squared is finite, then, oops, sorry, it was the reverse. Then one can write, just differentiating this guy, 1 plus iz mean value minus z squared over 2 mean square plus smaller, something smaller. Okay, so if it was 4 moments, then you can write down 4 terms in this expansion. And this is nothing but just differentiating of this expression under the expectation. Okay, so that's more or less standard theorems from the calculus course. Okay, good. So that's about the characteristic function. Then the next reminder is convergence of random variables. So probably you remember that there are many notions here, like almost sure convergence, etc. What I'm interested in is convergence in distributions. In distribution. Also known in low or weak convergence. Actually, this is the only reasonable notion when you do not assume that all the random variables you deal with are defined on the same probability space. So if you have, say, a sequence of variables defined on the same probability space, on the same omega, then you can invent meaningful definitions, like what happens point-wise, what happens uniform, etc. But if you are just given a sequence of random variables, each of them being defined on its own probability space, then basically this is the only reasonable notion. So what does it say? It says, okay, a sequence of variables converges. I will use this notation with just d upstairs. Converges to xi. If, meaning if and only if. Yeah?
Is it true that if psi is identically 0, then the characteristic function is 1?
Yeah, good point. Yeah.
It does not tend to 0. That it tends to infinity.
Oh, yeah. Yeah, sorry for this. Yeah. Sorry. Okay. Yeah. Thanks. Well, I was just thinking about Riemann-Lebesgue lemma. Yeah, thanks a lot. And be careful with me, so that, please look on these things. Yeah. Well. Okay. So this convergence in distribution, if and only if for every bounded and continuous function. These expectations do converge. Okay, so you can think about, for instance, just the function which is a constant, then this is a meaningless statement. I mean, if the function is constant 1, then 1 it indeed converges to 1. Okay, but of course you can think about more interesting functions. So it's tempting to think about this function being just h of x being x, right? Then we would get the expectation. The problem is that it's not bounded. So in general, you cannot play with that. If you know that the values of xi's are uniformly bounded, then you know that the expectations do converge. Otherwise, so this might be not the case. Okay, so why the name weak convergence? So mark. This is equivalent to say that the corresponding measures on the real line, which are just push forwards of measures here. So you take your probability measure here and you think what is the distribution of the values. So weak convergence of the measures, let me call them the fnx, where this is just the probability of xi(n) being smaller than x. It means that these measures on the real line weakly converge to dfx. Okay? So, well, there are many basic examples of these conversions. Then what is important is that there is a theorem, which as far as I understand is due to Paul Levy, as many other theorems in this business, that basically tells you a very nice description of this convergence in terms of the characteristic functions. So it says that a sequence of random variables converges to xi in distribution if and only if the characteristic functions of these variables converge to the characteristic function of xi pointwise, basically. So for any z. Okay, I mean from left to right, this is just a part of the definition, because what I play with, this h, is just the continuous bounded function here. So I just take this exponent and that's it. So what is the meaningful part of the theorem is the inverse implication. So, and for the inverse statement, you can also wonder, okay, if I'm just given this sequence of functions and I know that they do converge to something pointwise, do I know that this is indeed the characteristic function of some random variable? So this is a meaningful question. Here it's implicitly assumed that I already have xi, and so I already have this phi of z. So if we do not have xi here and only limit here, then you should also impose some continuity assumption on phi. And actually, you can, it's enough to impose the weakest possible, which is just continuity at the origin. So otherwise, bad scenario may happen. And the crucial point, just to remind you what can be bad, I mean, what can go wrong, is when the sequence of these random variables is not tight, which means that they take, well, roughly speaking, bigger and bigger values with constant probabilities. So if you know they are tight, then there is no problem with this. But anyway, so conceptually, this characteristic function is just a very useful tool to study convergence of random variables in distribution. Okay? Are there any questions so far? So if it's fine. Please ask and try to find, stupid things like here. Okay, so what is the next reminder? Is that there is a big theorem, which of course everybody knows from the basic course. So it says if we have a sequence of identically distributed independent random variables, identically distributed, and well, they have bounded second moments. Okay, they're all identically distributed. So basically, I can just say that this finite second moment, they're all the same. Then if you sum all them up to some n and subtract their mean value and normalize by square root and some other constant, then what you have in the limit is a random variable with a standard Gaussian distribution. So what are A and sigma? Or maybe it's, okay, let it be A. So A is the mean value. Sigma is the standard deviation. So sigma squared is here, and N01 is the standard Gaussian distribution. So Gaussian with density P of x 1 square root of 2 pi e minus square root over 2. Yeah, and then I apologize for this. I'm going to remind you the proof of this theorem just because the first result we are going to prove in the course is exactly of the same shape. Just let us let us remember how it goes. I mean, yeah, this is very easy, of course, but still. So as you might guess, or just remember, guess from the introduction, the only thing one should do is to write down the characteristic function of this object and to see it converges to the characteristic function of this object. So the proof. So if I have the characteristic function of this distribution, so they're all the same, then if I denote this, okay, let me do it a bit slower. So then first it's convenient to subtract a. Just don't care about a. So then the characteristic function of this guy is, of course, nothing but this. And then we know that it has, we can write down the local behavior near the origin. So it's given by d squared over 2. And then the mean is now 0, so we just have sigma squared. Okay, then we sum n copies of these, and they're all independent. Because of that, characteristic functions are just multiplied. So, and make another normalization. So what we see is that the characteristic function of this random variable well, what's here? Basically, first I should plug into this formula z over square root n sigma. So that's why here. And then I should power it to the n. Okay. And then, well, this is nothing but this experiment. Basically, that's it. That's the end of the proof. So this is the characteristic function of the standard normal distribution. So, okay, quite natural proof, and hopefully, well, now everybody remembers how it goes. So, again, just to make some comment on the content of the course. So, as I said, we're interested in, well, some objects which are simplest possible in some respect, but nevertheless, these are random paths. Say random curves, or in one dimension you can think about, and we will think about just random functions. So the corresponding theorem, there is the corresponding theorem. It's going to be maybe on this third lecture, or yeah, something like that. That the trajectories of graphs of random walks, they do converge to Brownian motions. And the idea is, is quite similar. So this is, in some respect, a version of central limit theorem, but not for real valued random variables, rather for random variables with values in some functional spaces for random functions. Okay, but here that's, the very clean example. And then yet another reminder. That's about Gaussian vectors. Should we open the windows? So it's going to be in the first set of exercises, and for exercises, the person responsible for exercises is Marianne. She's sitting here. So in the first set of exercises, there is something about Gaussian vectors, again, just to remember how it goes. So what do I need here? So what is a Gaussian vector? This is, you know, in a sense, an intermediate step between random variables, real valued or maybe complex valued, and random functions. So those are random objects in some finite dimensional space, say RD. And it's called Gaussian vector if any projection of xi on a line, so you just fix some direction in RD, some coefficients, if for any coefficients, this linear combination is a Gaussian variable. So this is the definition. There is an important point here. So what is the point? An example, it's fairly easy to construct an example. Just take all the components of xi to be Gaussian and independent. J. Okay, so we can just construct this multidimensional random variable, and then, of course, each of the combinations is again Gaussian, because the sum of two independent Gaussians is again Gaussian variable. The message is that, in some sense, this is the only possible case. But of course, one should be careful writing this on a blackboard, because literally speaking, this is not always the case. This is always the case in some bases. So the other way to see this story is to start with densities, like here. So an alternative way to say what a Gaussian vector is to say, okay, alternatively, is to say that there is a density which is now characterized. In the scalar case, we had just one number, which is the mean value, and the other number, which is the variance. And in this case, the mean value, okay, it must be a vector in RD, because all the values are there. So, and we also need some replacement for the variance. And the natural replacement is a D by D matrix. So which I'm going to denote by G for some reasons. It's rather similar to sigma, right? So it's going to be G. Well, okay, if I put here capital sigma, then, you know, with summations, it's not very useful. So, and then it should be exponent minus 1/2 x transposed G minus 1 x. Yeah, and that's, yes, sorry for this. It should be also mean value somewhere, right? X minus A transpose 3 minus 1, X minus A. Okay, so what is what here? So A is the mean value. This is a vector in RD. And G, well, this is again simple exercise. Actually, this is the covariance matrix of these random variables. So this is xi minus A transposed xi minus A. This is the matrix. So here, I think about elements of RD is about columns. So here is a column, here is a matrix, and here is a row. So I just multiply all them, and what I have is a number. Okay, just about the notation. So from this description, say if we start from here, then one can think about the remark above as following. So I'm given some matrix, which is by definition is positive and semi-definite. So from here, this is almost obvious. And then in some basis, it has a diagonal form. So this is just the very basic fact from the linear algebra. So for any matrix G, I can find a basis such that it has a diagonal form there. And then this is a sort of an exercise to prove that indeed we are back to this construction with independent Gaussians. And this is mentioned in the set of exercises. So if you are not very familiar with this by some reason, then you have an opportunity to discuss. OK, so I think these are all the reminders I had in mind. And in the remaining 7 minutes of the first hour, let me discuss the notion of stochastic process, of a stochastic process. Okay, so let it be paragraph 1 with the tentative name stochastic processes with independent increments and continuous trajectories. Well, yeah, again, to the contrary, say with Ivan's course, there are no lecture notes, actually, for this course. Actually, the material is quite standard, and there are several textbooks on this. So if you, well, the names are, okay, there are very formal books like Kallenberg, for instance, Introduction to Modern Probability, or you can read Stokvaradhan, I don't remember the name, though. Or there is a book by Oxendal, which is a very classical reference, though some proofs are missing there. Anyway, so if you need something precise, you can just ask me in private, and we can discuss what is your level and what is more suitable for you. And because of that, the names of chapters are going, to be a bit artistic, whatever. So let us discuss the definition of a stochastic process. So we have some probability space, as usual. So it's going to be a random object. So this is the probability space. And then it's going to be a variable called t, which I think about being a time. So I think about some evolutions. Just a comment on this. In principle, this is not the only possible viewpoint. So in particular, again, in the second term, during the second term, another very fundamental object will appear, which is called Gaussian free field. And about this, you can think in a very similar manner, but then T is two-dimensional, so there is no natural direction of time, and moreover, it's more complicated structure. But I'm going to think about evolutions in this course. So, okay, let me also fix some capital T, which in principle might be plus infinity even. And then I'm thinking about objects, which I'm going to denote this way. Again, I'm going to write 0t, but it could be also not including the capital T, in particular at infinity. There's just a slight abuse of the notation. So I'm intended to write t, but okay, well, t was included, but it's not necessary. So again, it's called a stochastic process.